Hey everybody, this is Super Testnet, and I just recorded a whole workshop on Cashew and Cashew mints. And I got to re-record the first 14 minutes because by accident we weren't recording the audio. So the audience is left, and I'm just going to redo the first 14 minutes of that recording so we have the audio. All right, thank you for coming to the Cashew workshop. This is what we're going to be learning about today. Cashew is an awesome protocol for doing Bitcoin banking stuff. And here I have a little representation of how it looks. We got a server. That's what a server looks like in my world. He's blind. He can't see anything because we use blinded servers. I'll tell you what that means later. He's passing out these things called ecash notes to all these happy people over here, and I just love it. So that's what we're going to learn how to do today. If you want to follow along, I recommend you do that because we're going to have some code. We're going to have code in here. We're actually going to build a little wallet. So if you want to follow along, you'll need the code. And to do that, you can just paste this into your browser and check it out. It just pulls up the full presentation right here, and then you can follow along that way. The other thing that I recommend you do is not just pull up the presentation, which has the code in it you're going to need, but also pull up the GitHub because this GitHub project over here has like the final product that we're going to make. So we paste it, and this is what it's going to look like. If you click this, we have a little wallet over here, right? And this is pretty basic, send and receive. But in a few seconds, check this out. This is about to change. 256 free sats show up in your wallet. Just kidding. These are fake. These are not real money. But yeah, we're gonna show you. I'm gonna show you how to make this wallet, and then right here inside of this group, you'll be able to send and receive 256 sats to and from each other, and it'll be great. So this is what we're gonna build, and let's get started. All right. So what is Cashew? Cashew, well, it's pretty cool. Let me tell you. Cashew is a free and open source chaumian ecash system for Bitcoin. This name right here is probably unfamiliar to some of you. David Chaum is an altcoiner. No, that's not true. It's kind of true. Before Bitcoin, David Chaum, back in the 1990s, kind of invented cryptocurrency. He was like this really cool guy. He made this software that he made it for banks to use, where they could interact with their customers using this Xiaomi and eCash software, and they wouldn't actually need accounts. The customers didn't have to have accounts with the bank. Um, the eCash system would allow you to make deposits and withdrawals without actually having an account. It was great for privacy and stuff. Didn't exactly take off, like you did a pilot and stuff. Anyway, now that Bitcoin's around, we've recreated it. Oh, and I wanted to mention something because eCash is actually mentioned in the Bitcoin white paper. I think this is pretty cool. If you go to bitcoin.org, and then you go to bitcoin.pdf, this isn't in the slideshow because I didn't realize it until today that I should bring this up. Bitcoin actually mentions David Chaum's, well, he mentions eCash in general on page 2 down here. He talks about right here. The problem, of course, Satoshi says, is the payee can't verify that one of the owners did not double spend the coin. He's talking about eCash tokens when he says coin here. A common solution is to introduce a trusted central authority, or mint. And mints, that's what the Cashew software is. Cashew software creates this thing called a mint, an eCash mint, and they do what he says. They check every transaction for double spending. Right here, this sentence says, after each transaction, the coin must be returned to the mint to issue a new coin, and only coins issued directly from the mint are trusted not to be double spent. That's what we're doing today. We're going to build this eCash software, or not, we're going to build the software. We're going to build an eCash wallet that trusts a mint to check if coins are double spent. And it's pretty neat. It's one of the things that's really cool about it. Centralized solutions like this, they bring the benefit of speed. Like this software that we're going to show is as fast as the Lightning Network, or actually it's even faster than Lightning because you're just moving entries around in like a database. But of course, that comes with problems. And one of them is what he mentions right here. The problem with this solution is that the fate of the entire monetary system depends on the company running the mint. So, no pressure. You're just upholding the fate of the entire monetary system, or at least of the people using your thing. So, with every transaction having to go through them, just like a bank. So, there are problems with this software or with this solution. Mainly, it's trust. In fact, it's only trust. It's always the problem in Bitcoin is who you're trusting. Here you're trusting the mint. If you have a trustworthy mint, good on you. If you don't use that mint because it's not trustworthy. Anyway, that's Bitcoin is like a solution to all this, but mints are cool too. So we're gonna build a mint. Mints are custody software, but they do have three cool properties. They have rapid payments internally, like it's faster than Lightning. They have pretty good privacy because I mentioned earlier you don't have to have an account, and that's true here. And they also have built-in Lightning support. And I'll show you how they do all this stuff today using Cashu API, which you can use if you're a dev to add Cashu or ecash to your Bitcoin application. Pretty sweet. So this is a graphical representation of an ecash wallet. And I have actually got one pulled up right here that happens to have 50 sats in it. So to get the sats onto there, I had to click this create invoice button, and I created a invoice for 50 sats, and it showed me that QR code, which somebody in the audience paid earlier. But we don't have to do that. We can just pretend it's been. Oh wait, did you just do it? Well, how's that happening? I don't know. Someone paid it, so we got 100 sats now instead of 50. And when you're gonna send somebody ecash, this is what it looks like. Let's create one for 40, and I will click send, and it gives us this little string. This little string is effectively a check or a money order drawn on the bank's vault. Um, and if you give this to anybody, then the mint promises to give them 40 sats in this case. So you just copy this, close it. You'll notice I only have 60 now instead of 100, and I could send this to somebody. They would click receive, paste it into there, and now we're back to 100 because that's ecash and it works really easily and great like that. So you notice that this is faster than regular Bitcoin. It's faster than the Lightning Network because it's no pathfinding. You're all just interacting with the same mint, so it's faster unless you have a direct. If you have a direct Lightning connection with someone, it would be just as fast as Lightning. But ordinarily you don't, and so this is faster. Cool, faster than Lightning, but trust. It's not like Lightning, and it's not like Bitcoin. You have more trust assumptions. You have to trust whoever's running the mint with the fate of the entire monetary system. All right, so that's what that looks like. Let's suppose that we weren't using a Cashu mint, we were using a normal custodian like Coinbase. Let's suppose Coinbase wanted to replicate that user experience we just showed. How they might do it, is to give every user an account. So here we've got account number 452 and account number 811. The first account, 452, has 50 sats, and the other account has 0. So then the Coinbase could give you a button to create one of those little strings, and then they're going to deduct the 40 sats from his account, and then once the other user pastes the string into their account, it'll add 40 sats to them. And there's a few drawbacks to if Coinbase did this. One of the drawbacks is you need an account. Like Coinbase isn't going to give just anybody money. They got to do KYC on them. You need to sign up with like a username and password so they can contact you. And I didn't have to do any of that with the Cashu wallet. I just visited this website, cashu.me, and it just happened. So that's a benefit of using these types of systems. They're more private. So how could we improve on this model where there's accounts, and turn it into something more like Cashu? Well, the first improvement we could make without doing any of this the blind signature stuff that I'm going to show you later in this presentation, Coinbase could get rid of accounts and just create vouchers. Like everything would be a voucher. So let's suppose in this hypothetical example, Coinbase got rid of the accounts, and if you want to deposit money to Coinbase, they just give you a QR code. They say fund to this QR code or send money to this QR code. You send it 50 sats, and it just gives you a voucher. It just gives you the string. No account. They just issue a string. We're going to call it voucher number, some random number over here, and that's your string, or that represents your money. And then if you want to send somebody money, you just paste it in there again. You paste your existing string and you split it. You say, I want 10 that I'm going to give to somebody else and 40 that I'm going to keep for myself. Like you could do that and Coinbase could replicate this, but it wouldn't be perfect. One of the problems with this attempt to emulate this system over here is although you don't exactly have accounts, Coinbase knows when it issued each voucher. Just like Walmart knows when it issues every what do you call it? Every gift card that Walmart creates, the Coinbase would know every time that it issues one of these things. And why is that a problem? Well, let's just suppose that there was a protest going on in Canada with a bunch of truckers who were trying to receive money to sponsor their protest. And the Canadian government went to Coinbase, we're assuming they're using this voucher model, and they were like, we need you to shut down their accounts. Well, Coinbase could legitimately say, we don't know who they are. Like, they're just, we don't have accounts. We just create and redeem vouchers. We don't have any user info on these people. But the Canadian government could say, okay, well, we do know that there's a huge spike in activity on the day the protest started. So for the next until the protest is ended, we need you to stop redeeming these vouchers. And Coinbase they could give them that information about like when the activity started increasing, and they could actually do this because they know exactly which vouchers are trying to be redeemed. They could say all the ones since January we're going to get rid of. We're not going to redeem them. Uh, ecash tries to fix that by getting rid of the timing analysis, by getting rid of the timing information and getting rid of the amount information. So in Cashu ecash, the issuer, the mint, he creates these. I think I can stop now because this is the slide where I picked up again, right? Oh, okay. So I'm gonna keep going for this slide. Uh, so the mint creates um, a bunch of different tokens here. Let's say 1 sat, 2 sat, 4 sat, 8 sat. He creates them in powers of 2, and every user of the mint uh, issues ecash. They send in amounts and get back tokens in one of these powers of 2. This prevents you from having analysis of people's account information based on how much money they put into their voucher. So it's not like a specific amount. Everyone's got these round amounts, these powers of 2. And then the other thing they do is they issue them in huge batch. So the mint behind the scenes, when it starts up, it creates, I've got like 3 examples here. So it creates 3 1 sat vouchers and 3 2 sat vouchers, 3 4 sat vouchers, and whatever. And it's using these things called blind signatures that is attaching to every token. And a blind signature is useful because there are 2 versions of that signature. There's one that's valid for the original message, and a second version of that signature that's valid for a message that the mint has never seen before. And we'll get into how that works in a minute in the next few slides. But this property where you have 2 signatures that are both valid for the mint means that when you go and redeem your token, you show them a signature that they've never seen before. But they can check it and see it's valid. They can check and see that I know this signatures comes from me, like I created it, but I've never seen this message before. Using a trick I'll show you in a minute, they do know the value. They do know the value of the token that you're signing against, or not that they signed against. So they can redeem it, but then it's no good. There's no other signature that can be created from their original one. So once the signature's been shown, they reject. They say no further redemptions for that token. So this allows them without this disrupts the timing analysis. Once you redeem one of these signatures, the mint doesn't know which batch that token was issued in. It could have been issued at the beginning, could have been issued at the end, and so if the government wants them to say stop issuing ones from January forward, they can legitimately be like, we don't know when, we have no idea which ones are being redeemed and which ones are being were already from before. So that's an improvement. It's an improvement on privacy. And let's talk about how this works. Let's talk about how blind signatures work. Blind signatures allow somebody to sign a message without seeing its contents and verify later that they signed it. I'm going to use the analogy of carbon paper. Have you guys ever heard of carbon paper before? It used to be used before copy machines existed, where you'd have a piece of very thin paper that had been treated with carbon on top of a thicker piece of paper. And both of them would have the same contents, but you'd lay them right on top of one another. And if you used a pencil to sign, the top document, the carbon would be pushed down by the pencil and would transfer to the copy underneath. So you'd be able to sign 2 things at once. And this was done by banks. They would have you sign it once, and then they'd keep a copy and give you back a copy. and that was carbon paper. Some people use this to make blind signatures for elections. So they will have you, when in an election, you will write out who you're voting for on a piece of paper, put it inside an envelope that's made of carbon paper, and then they will have an election official sign the envelope. And they don't know what you wrote because it's inside the envelope. They don't know who you voted for, but they use this to say, "I do know this was a valid vote. I know he voted because it's got the election official signature on it. But I don't know who we voted for." When they open it up later, they can see, okay, here's who got voted for, and we know it's a valid vote because it's got the election official signature. But the election official never saw who you voted for. So that's what blind signatures are in the real world. And in Bitcoin, we figured out a way to do them. Or, well, I suppose David Chaum figured out a way to do it before Bitcoin, and then Bitcoin copied it, or Cali copied it. But does everyone see? Sorry, before I get to that, does everyone understand this concept of why that would be useful? Blind signatures, not knowing what it is you're signing. Cool. So in Cashu, signatures are points on Bitcoin's elliptic curve. Just like Bitcoin public keys, there are these long strings of random numbers and letters. And when you create one, you actually create it together with the mint. So we've got the mint over here. He's a blind server. He was going to create a note together with Bob. And Bob and the server created together by doing this. He gives the mint a pub key. The mint adds another pub key to it using this cool thing called, which I'm about to get to in another slide, in the next slide, called key addition. And it produces this thing, which is a key that both of them know about. So this is the blind signature. And then Bob, is going to use something called key subtraction to produce the unblinded signature, which the server has never seen before. But because of this thing I'm about to show you, the server can understand it. Blind signatures, once you have them, users treat them as money. Bob effectively purchases a blind signature from the mint. That's when you deposit 50 sats, and he gives you a 50 sat token, or I guess it would be a 40. What's the power of 2 there? 32 and 16. 32 plus 2. 32 plus 16 plus 2. Yeah.
It's like with binary clock.
The question is it like a decimal clock or a binary clock? I don't understand the question. But if you wanted to do 50, you'd need 32, 16, and 2. Because that sums to 50 using powers of 2. Anyway, he bought 3 tokens, and then if he wants to use them as money, he sends those tokens to Alice, along with the private key he used to help create the blind signature. And then Alice is supposed to redeem it immediately. She's supposed to go right to the mint and say, I want a set of 3 new tokens, ones that Bob doesn't have. And so she just swaps them. She swaps the 16 for another 16, the 32 for another 32, the 2 for another 2, and now Bob can't do anything because if he tries to go and use his copy, the mint will say, sorry, this has already been spent. The question is it like a gift card? Yes, it is like a gift card, except a gift card, the issuer knows when he created it, and these things, because of the timing analysis trick with blind signatures, they don't know. Question is? That is correct, but I can't repeat it for the camera because he was asking the question was about all of the information that goes into a token. It includes the pub key of the mint and includes the pub key of the user, which are combined using key addition into one thing. And I think that answers your question. Is that right? No. But if you do, you can. The question is, when does the information about the amount get into the token? That has to do with the mint's public key. So for each of these amounts, the mint maintains a different public key. So for this amount, his public key will be A. For this amount, his public key will be B. When you show the blind signature, he tries to validate against each of his public keys, and whichever one it validates against, that's the amount. So that's how that works. Does that make sense? Isn't that cool? And that's a cool idea. Without seeing what the message is, he does know what the amount is, which is cool. Okay, so that's those things. So she swaps it, and that ensures that Bob can't double spend it. You can also swap it for Bitcoin. You can either swap it for another blind signature, or you can say, "I'm ready to withdraw," and the mint, suppose as long as he's honest, he lets you withdraw, as long as he's trustworthy. The fate of the entire monetary system depends on this blind little computer over here. Okay, so key addition. How does key addition work? Blind SIGs take advantage of this property. It's a feature of, I think, all elliptic curves, but I've only really studied Bitcoin, so I don't know if it's. I'm pretty sure it's part. I think it's an inherent part of elliptic curves. Yeah, this guy knows what he's talking about, and he says I'm right. So there you go, viewers. Smart guy says I'm right. So we're gonna invent a simplified public key system, which we're gonna call. I don't know. What do you guys want to call it? The simplified system. Super secret. We'll call it super secret. Super secret. In the super secret elliptic key system, a public key looks like this, 1, 2, 3, and a private key looks like this, ABC. Not very secure, right? But let's pretend. We'll pretend. Here's another one. 4, 5, 6 is a public key. DEF is a public key. Cool thing about elliptic curves is if you add these two public keys together, 1, 2, 3, 4, 5, 6, it's still a valid public key. You can send money to that. You can receive money from it. You can sign messages with this private key. It's great. And the private keys, similarly, if you just add them together, they're all just numbers. You can add things with numbers. It's valid for this public key. That private key can sign for this one. Really cool property. This is used in the cryptography of making blind signatures work. I don't understand the cryptography, so I can't explain exactly how, but I saw in the code base they use this. What's up? Yeah, I know that's a factor of key system. The question was, why is this key so long? It's because I didn't because it's super simple. When you add normally, yes, it uses clock math, which means it goes if it overflows, it goes around to the small side again, and it remains the same size. So in key addition, you don't get this property in a real system, only in super secret system. Okay, next one. The other thing it uses is shared secrets. Blind SIGs use point multiplication, which is different from addition, totally different mathematical function in these things, which allows two key holders to produce a shared secret. So here we've got 1, 2, 3, and ABC again. If you multiply 1, 2, 3, this public key, by this guy's private key, you're going to get a different private key, KB0. And if he does the same thing, if he takes 4, 5, 6, which is his public key, and multiplies it by ABC, your secret key, he's going to get KB0. And you can use this to create shared secrets without disclosing your private keys to each other. Like, I don't have to show him my private key, I just have to multiply it by his public key. And he does the same thing with his. He multiplies his private key by my public key, and we'll get the same shared secret. So I see this in the code base, this elliptic curve multiplication thing. And so I know it uses it, and it's pretty cool, but I don't understand more of it other than to say blind signatures involve creating a shared secret and then subtracting it later, and then you get a separate message that he's also signed, but he didn't know he signed it. It's freaky. Freaky, but it works. Okay, so that is as far as I can get with explaining to you how it works, because now I want to build one. You guys ready to get out your computers and build a one of these wallets? Let's do it. So normally when I make these presentations, I am weird in that I don't use frameworks, I don't use React, I don't use all these fancy things. I build everything so that it can work in the browser. And one of the reasons I do that is because when I'm doing presentations like this, you guys don't need to download anything weird. You have a browser, you need a text editor, and you can follow along. So open up a new folder. I'm going to create a folder called super secret. I'm going to call it this might already be a folder, but we'll see. We're in luck. It wasn't already a folder. Okay, so enter your super secret folder or whatever you're going to call it and create a new document, and we're going to name it index.html because then it shows up pretty when you upload it to a server. They like it when you upload index files. So we're going to do that and open it up in a text editor. I'm using Sublime. That's my preferred text editor of choice. You don't have to use Sublime. You can use anything that can edit text. I've seen people do this with Notepad. I've seen people do it with Visual Studio, whatever you like. As long as you can edit text, you'll be good. First thing you're going to do once you have done all those things, So like by now we're at the fifth thing you're going to do is paste this code from our slideshow into your index.html file. Paste it, save it, and now let's open it up in our browser. You can right click it and say open with whatever browser you use. I'm using Firefox here. So I do that, and look, we're partway done. With that simple couple of lines of code, we've got something that looks like a wallet. Of course, it doesn't do anything, and there's no code for doing anything, but it's a start. We got somewhere, right? So, is everyone with me? You all got this on screen? Great. Next thing we're going to do is we're going to make it do something. We're going to add some libraries that we need in order to run this code. And I made a mistake here when I said what libraries to use. I'm going to replace my head file with this one I just copied. I said that you need SHA-256, and after you've imported the SHA-256 library, I made this wrapper around it so you can pass in strings, because the original one only accepts bytes. And then I found out today I don't actually use this anywhere. So feel free to just delete it. You don't actually need the SHA-256 library because I never ended up using it. Yay! Simplified code. One less library. In fact, I'm even going to delete it from here. I don't actually need it in the presentation at all. So no more need for SHA-256. All right, so now we've got our dependencies. We need a few more things. We work with hex strings a lot in Cashu, or in ecash, or, well, in Cashu. I don't know if this is true for the other one. So I'm going to add a little function called isValidHex. And this function, if you pass it a string that you think is hex, it will check if it is and then return true or false. And so it's nice. So we use this later because of the way Cashu identifies its public keys is using hex. And we can check if they're valid. The next thing we need is a couple of things for doing hex transformations. We need hex to bytes, which takes a hex string and turns it into an array of unsigned 8-bit integers. We need the thing that does the reverse of that, takes an array of unsigned 8-bit integers and returns it to a hex string. And then we need something called hex to text, which we use because Cashu likes to create these things called secrets in text format and then turn them into hex, and then we'll end up turning that into bytes. So that's what we need those. So I'm just going to copy them and drop them in right under is hex. That's where I'll go. And then the third thing we need is wait a sec. This is a little function that I wrote that lets you specify a number of seconds you want to wait before you proceed, and it'll do that. It's kind of like sleep. If you've ever used sleep in Bash, you can make your program wait till tomorrow to run again. We're going to use that to do a loop later so we can check if an invoice has been paid and not DOS the mint. So we pop that in there, and now we can make our program sleep for a second, or however many seconds we want. By the way, I find this function really useful. If you don't already have something similar in your JavaScript programs, looking at you, you should, or Jose, I mean, you should copy that because it's wonderful. Well, it gives you sleep, access to sleep, which is like a built-in thing in Python, but JavaScript you need to write it. All right. So, what? What for this? Yeah, so you have to do promises in order to sleep, or at least I don't know if you have to, but that's the way I figured out how to do it, or someone told me to do it that way. All right, so once we got all our dependencies, let's refresh our page now and see in our console if we got any errors. In mine, I did not get any errors, and that's great. If you got an error, it'd be red. You'd see a red thing, or, well, Firefox would show you a red thing, and it would say you did something wrong. But I like to stop every now and then, make sure I didn't have any typos or mispaste something or whatever, miss a script tag. Just doing that. All right, next. Next thing is a self-executing function. These are things I learned about like 6 weeks ago. Self-executing functions in JavaScript, you don't have to call them. If you just put them in your code somewhere, they'll run automatically. So I'm going to put it at the bottom of my page. And this is a trick I learned. If you don't put it at the bottom, then if you like try to modify this button or something and it hasn't loaded yet because it's running up here, it'll throw an error. So I always put these self-executing functions near the bottom of my page. And then this is going to create a secret for us that we're going to use to create this blind signature, and it's going to log it. So let's save that and run it. And we should see, yay, we got a little log here. Look at that. We have created a secret, and we're about to use it to create a blind signature. And if we refresh, it'll be different every time because I'm not saving it, and you don't really need to save it. Or maybe you do. Yeah, you do need to save it, but I'm not. Okay. Next thing we're going to do is we're going to add to our little function. So I have here a couple of dot dot dots, and if you see dot dot dots in this thing, that means don't make a new one. Just use the one you already have. So I'm going to put step 2 on here, and I'm just going to put it right under step 1. Paste it. And what's this doing? Well, this is going to reach out to a Cashu mint called testnut, where everything's free and the points don't matter. It's going to save that endpoint in local storage so we can use it when we call our send button later. And it's going to fetch something called Keysets and log them for us. And let's go take a look at what Keysets look like by refreshing our page. So we do that, it reaches out, and it gets this thing called Keysets. So every mint has a thing called Keysets, which they identify using either a hex string or whatever that format is. I think that's probably base 64. They identify them using one of those. And this key set has the list of public keys for every amount that they support, for every power of 2 up to like 900 quadrillion or something like that, some ridiculously high number. So these are going to identify the set of public keys that we're going to use to create a blind signature for a specific amount of cryptocurrency, of Bitcoin. With me? All right. We got key sets, and then we picked one. The other line of code just picks the one that is all hex, and that's what we used the is valid hex for. This one failed the test, and this one's hex. I don't know why there is a one encoded in this format. Every mint seems to have one, and when I asked Kelly which one I should use, he said use the one that's in hex. So that's what Kelly told me. That's what I'm doing. All right, so that's what that's there for. Or I don't know why it's there for, but that's that. The next thing, now that we have our key set, we're going to fetch all the public keys listed under that key set because we're going to use one of them. Well, more than one, but in this case, we're going to use the one corresponding to 256. So let's take a look and see what we get. So now, if I expand this out, and probably have to make it smaller. Yeah, okay. So take a look at this. We've got a whole bunch of public keys in here, one for every power of 2 from 1 all the way down to some giant number that, but it's more than 2 to the 32. This is like it's the maximum value of a JavaScript in the current version of JavaScript, I think. But yeah, these are the public keys that we're going to create blind signatures that are so that our unblinded signature is valid for one of these public keys. And the one that I'm going to use, the amount we're going to use today is 256 because I like that number and it seems like one that's fun to send around. I'm going to send 256 sats around. In the future, if you're going to make a more advanced wallet, you're not just going to use one of these numbers. You're going to have to make it so that they can pick any one of these numbers and get whatever amounts you need for all these. But in this basic example, we're just going to get 256 sats from the mint and then send it to each other. And that's it. That's all we're going to do. All right. So we have our list of public keys. We can get one from over here, and the amount that we're going to use is 256. So we should see that the amount public key for 256 corresponds to 0296D2. And if we just scroll up there and double check, the number 256 is indeed 0296D2. Great, that's the public key we need in order to create a blind signature that is valid for the 256 sets. And so that's what we do next. I think it's what we do next. No, we need to get an invoice for that amount. That's what we need to do next. Okay, so we need to pay the mint to give us a 256 sat token with his signature on it. So that's what we're going to do here. I'm going to create a little post data function object that says I'm making a post request. I expect you to give me back application/JSON, and the amount I want you to give me is 256 sats. So I'm going to pass that to the Mint, and he's going to give me back a Lightning invoice, and we're going to log it. So let's do that, and we'll refresh. And what we should see down here is an object that he returned to us containing an invoice. So this is, don't actually pay this on Testnut, on the Testnut software. These Lightning invoices are automatically paid. Like he just automatically considers them paid, and he credits you with. He's gonna give us 256 sats, fake sats. So you don't actually have to pay this, but in a real wallet you would need to. So in order to make that easy, I made a little looping function. This is what we use wait a sec for, and that's what we do here. We just loop until it says it's been paid. So this function says pay this invoice. It's going to give us the invoice that we just saw. It's going to wait 5 seconds and then query this endpoint to see if it's been paid. And if it hasn't, it's just going to loop back and keep doing that every 5 seconds. So we'll do that. And what it should show, pay this. And then after 5 seconds, it should move forward and says, yeah, it's been paid. Because on testnet, they're automatically paid. Cool, huh? Now you know how to do loops in JavaScript. Very useful. This guy's learning JavaScript for the first time. Well, for the 8th time. Uh, Not for create. So the question was, it looks like a lot of these functions, including the one that creates an invoice, comes from BlindSig.js, which is a library I made. And the answer is no, not that one. The BlindSig.js does not create that invoice. It queries this endpoint from the Mint, and then the Mint creates the invoice for us. BlindSig.js is a library I made that creates and validates blinded signatures. Well, in fact, I didn't even make the library. Gandalf BTC, thank you for watching. He made it, and then I ran it through Webpack because he made it for Node.js, and I wanted to use it in the browser. So BlindSig.js is just his code made it compatible with the web browser. Great. So we're good. Continuing on, the next thing we do, now that we have a paid invoice, we request from the Mint, we request a signature that is valid for the amount 256. And we use every invoice on this thing comes with a quote ID. They call it a quote ID. And we pass that back to him and say, okay, I paid the invoice. Please give me a token with your signature on it for that amount. So here we go. We just paste it right here underneath. Save. And we should see our signature request in our browser. And we have to wait 5 seconds. And we can read what Dylan says while we do that. And here we go. We got our signature request. So we're saying, hey, Mr. Mint, I paid the invoice that has this identifier. Please send me a 256 sat token from the public key corresponding to number 256 in this key set. And here is my public key. Remember, we give him a public key and he combines it with his own. That's we're giving him our public key. Okay, so that's what we do there. And he responds with a blinded signature, which is his public key added to our public key. Here we go, using key addition. And using something involving shared secrets, which I know they use, but I don't understand much about it, but I can see why shared signatures might be useful. So what we should see here, after we pay our invoice, there we go, we should see him respond with a blinded signature. There we go. We have a blinded signature from the Mint that he says, if you unblind this and then pass me back the unblinded one, I will know that you have a 256 sat token. But they're single use. Once we've given it back to them, we can never use it again. Okay, cool. We're almost there. We just need to save that with our private key and unblind it. We have to unblind it and save it with our private key. And that's what we do right here. This code takes the blinded sig and uses, it converts it to from hex to a point in this elliptic curve library, which needs it to be a point on the elliptic curve. So once it has the point, then we get the public key that is valid for the amount 256 from the mint, and we use the public key and the blinded signature as well as our private key, which is inside of this message function, created it earlier, to create C, which is the unblinded signature. And then once we have C, we convert it from a point. We convert it to hex. That's where the 2-hex function is right there, because when you put stuff in an object and try to save it in local storage doesn't like points. It wants them to be hex. So I've turned it into hex. And then we get this. We get a little I call it a UTXO. I call it a UTXO because we interacted with a server's database, and when you interact with a database, that's a transaction. We got an output from that transaction, which is this unblinded. Well, we got a blinded signature, which we turned into an unblinded one, and so it's an output from a transaction, and we haven't spent it yet. So it's an unspent transaction output, according to Super Testnet. That's the terminology I'm going to use. I've already gotten people who are mad at me for that because it's a Bitcoin term, and you don't use Bitcoin terms and confuse people. But I do what I want, right, Joao? Right, Jose? So let's save it and take a look. Here is our Cashu UTXO after we wait 5 seconds for the invoice to detect that it's been paid automatically. There we go. There is our little unspent token. And here's the unblinded signature. If we can give this to someone, or we can give it back to the mint, and they will let us have 256 sats, or they will let whoever gives it to them have 256 sats. Whoever does it first. Pretty cool, huh? So we have 256 sats. The next thing we need to do is update our little balance here to show that we have some money. And so that's what we do next. I'm going to create a global variable. Don't do this if you're a real JavaScript developer. JavaScript developers hate global variables. Well, they love them, but if you talk to the good ones, they say don't do it. I'm a bad one, though, so I'm going to say go ahead. Create a global variable called UTXOs. We're going to put our UTXO in there, and then I'm going to import these two things. This dollar sign syntax comes from the world of jQuery. The jQuery people figured out this great way to grab elements from your web page using a dollar sign. It looks like this, and I love it. So I'm importing those, and then so let's do that. We're going to put those above our self-executing function. Which look how long this thing is now. We've written so much code, guys. It's amazing. So those are global variables, and then down at the bottom, we're going to add these lines that create the value 0, and then for every UTXO inside here, it's going to it's going to give us some money. So we do that, paste it, save it, and I forgot something. I have to add to this code UTXOs dot push our little UTXO. So I will add that to my code right now so that it's valid for other people who are doing this. Paste. Okay, now we save. Almost had a bug there, fellas. And we refresh. And what we should see is after we wait 5 seconds, this should update. Did it work? Yes! Look at that! We got it. Our wallet is working, guys. And we're so close to done. Okay. We have money. Now we just need to send it to each other. Believe it or not, that only takes like two things. Okay, so we're going to modify our send button now. And we're going to do this below our async function. By the way, is everyone with me? Does everyone have 256 sats in your wallet? Sweet. Okay. Copy that. And we don't need this stuff anymore. This thing that says close this function for now, but we'll add to it later. We're done adding to the self-executing function. So we can delete that. And we'll make a new function below it called send. And when we click on the send button, it's going to run this. It's going to reach out to our mint. No, it's not going to reach out to our mint. It's going to create something called a nut, which is one of those little tokens that say Cashu. the string of random numbers and letters. It's going to create one of those, which is an object. And for every UTXO in our UTXOs database, which is that global variable up above, it's going to add it to the proofs section because that proves we have a token, right? And then it's going to append Cashu A to it and stringify it and turn it into base 64 because that's what the format they like is. Then we're going to log our little thing, our little nut, clear out our balance because it's all in this little string now, and set our balance to 0. So here we go. Let's do this. Wait 5 seconds for the thing to update, and then all we got to do is hit send, and we should see, yeah, I hit send. Here's a little cashew nut, and we don't have any money anymore. It's all in here. Cool, huh? That was as easy as that's probably the easiest send button you've ever made in a Bitcoin wallet. Kind of a Bitcoin wallet. It's actually banking wallet, but whatever. Okay. Next thing we got to do is receive it. So I'm just going to create this receive button here, and initially we're not going to validate the token. We're not going to even check if it's valid. We just want to check if this function works. So we're going to prompt them to paste in a token, and then we're going to take that token out of the proof section of the cashew nut and put it into our UTXO database and update our balance. And we're not even going to validate whether the token is correct. So let's just do this, make sure it works, wait 5 seconds for the thing to pay. Maybe I should make that smaller so we don't have to wait 5 seconds every time. Yeah, I'm just going to go make wait a sec. Instead of waiting 5 seconds, we'll just wait 2. Yeah, well, yeah, I'll just make it 1. Why not? It says wait a sec. So refresh. And then it should, yeah, that was a lot easier of a wait. So we're going to hit send. There's our cashew nut. We're going to paste it into receive. Here we go. Oh no, token.token is undefined. Oh no, I don't know why this error is here, guys. We're gonna have to do some live coding to figure out why there's an error. All right, so let's do some console logging. Sometimes this stuff is really useful, even though it makes me sweat when I do a thing and I get an error, because it actually shows you how I debug. You think it's 147? I want to log the token. So let's create a little log for the token, and we will do send, grab our thing, receive, paste, and we see our token here. And yeah, I know exactly why this error is here, because I forgot that when you make this token, it is supposed to say when you create the nut over here, I did it wrong. It is supposed to be this token nut in an object. So that's what we need. And I've saved it so other people shouldn't have that same error happen to them. But that's what you need. So go and modify that line of code, or at least let's check it and make sure it works. Then go modify it. So let's check it. Send, copy this, receive, paste. No, it's still undefined. So why does it not like it? So what I wanted to happen there with token is I expected it to say token colon and then this object, but it is not what I got. So go back to here. So when I created that nut, it should show it right. Where does it console log the nut? Line 138. So where is line 138? There's the nut. I wanted to log it before it I know why oh. I think it's because I copied it into the slideshow and then didn't copy it into here. Token, save, refresh, make sure it works. Send, copy this, receive, paste. Well, we're closer. So we do have token.token in there, but it's then it says that's undefined. Okay, so this guy needs to be in an object. There we go. That's gonna work. So I gotta modify this as well. This guy needs to be in brackets. Live debugging of JavaScript. I think it'll work now. Is everyone with me? Let's refresh. Send our token. Receive our token. Fingers crossed. Worked. We have 256 sats again. Woohoo! We have send and receive, baby. That's what you need in a wallet. One thing we're not doing is we're not validating. We're not checking if this token is valid. He might have sent us one that is double spec. So to do that, we just got to swap it. You got to say to the mint, here's an unblinded signature for a 256 sat token. Give me a new blinded signature for a new. And you already did it. Cool. So we just do that by modifying our receive function. So we're just going to copy this stuff and paste it above this section that says this is a comment that we'll return to later. So we extract the secret, which is in our token right here. So there's our secret. And we make a new message and we say, okay, here's our message with our secret in it, or which we just create a new secret. Totally new secret. We don't extract it. We create a new one because we're making a new token. New token, new secret. Got it. We create a public key for it, and then we turn it into hex so we can pass it through the JavaScript library. And then what we do is we create a new UTXO output and save that. And we're going to create something called a swap object. And this swap object has as input the UTXO that we're getting rid of. That is the last UTXO in our UTXO set. We're going to grab that one. And this is how you do it in JavaScript because it's weird. And the dot length number is larger than the actual set. So you have to subtract one from it because JavaScript is weird. And then you put the new UTXO that you want that doesn't exist yet, but this one we're going to ask for a blinded signature for that. You put that in the output section, and then we're going to pass that to the mint. He's going to validate that our input is a token that has not been spent yet, and then he is going to give us a blinded signature for this UTXO, and then we're good. Then we'll have a new fresh one that has not been spent yet. So that's what the last section here does. We create a little post data and fire off a message saying, we expect you to give us a JSON that funds, this output using the amount that's in the input UTXO. So we pass it off to the mint, and we await his blinded signature. We haven't unblinded it yet, but we'll just look at the blinded signature. So let's do that. And we will send ourselves a cashew nut, receive it, and we will see a new error. Check it out. New blinded sigs is undefined. Why is that? So we posted a message to him, and he gave us back a JSON that contained signatures. So he thinks it was good. The mint did not give us an error according to our network tab here. He said, here's your signature. So that is the blind signature that we're looking for. But something in my code has an error. So what did I do wrong here? I said await the blinded sigs. It's 170. It's right here. I say new blinded sigs, and it should just say blinded sigs. That's all it was. I had a variable named wrong. tricks you up in JavaScript. So let me change that in here, save, and we'll redo this, and we should see our signature now. Send, copy, receive, paste, go. There's our blinded signature. Now we just got to unblind it and save it, and we are good. So that's what this next section does. It uses the same key set from the previous one. So it goes into our previous UTXO, gets the key set that it used, because we need to use the same key set from our mint. Then it goes and gets the pub key corresponding to 256 sats from the mint. The amount I want is 256, and it gets the pub key that he will only sign for 256 value tokens. And then the next thing we do is we use key addition and shared secreting to unblind that signature. Did I? No, I forgot to do this part. Copy this, paste it into our thing, paste. And then the next one is this guy. So we will copy him. We will unblind our signature. And then finally, we will add we will add it to our balance. So when we do this, when we run this, we should see we do send, we do receive, we paste it, and we got 256 sats. Woo! That's our wallet, guys. It is awesome, and you can send each other around to each other 256 sats by just giving each other these strings in Telegram or WhatsApp or whatever you like. And yeah, our wallet works. So we don't have very much time left because I think we want to keep these things an hour. But I just want to say for future work, for your homework, if anyone wants to do more with this, if anyone wants to do anything more with this, modify the send button to make it work with any amount. Like I'm just taking whatever value you have. Does it work? Jose. Woo! Things are working. So you got to make the send button work with any amount, not just whatever you happen to have. If you want to do future work, you can make the receive button validate all of your received UTXOs. Because right now I have this whole, this code down here that just gets the last one. And you see this a lot in my code. I just validating the last one. I'm not validating the other ones. So modify that, use a loop or something, or use for each to check that all of them are valid and not just one. That's some homework for you. Also, enable withdrawing from the mint. Like, we can send each other 256 sats all day long, but the mint still got our 256 sats, right? It's still in his database. How do we redeem it? Well, for that, I want to show you how in a minute, but I just want to say a few more things. You have to enable depositing to the mint, and you have to learn how to do this stuff, pub key locks and multi-sig locks. So I've got some code for all of this, but this one is particularly helpful. I call this code decompose amount, and I'm going to add it to the top of our document underneath the other libraries, and I will show you what it does. I wrote this code myself, by the way. I had to figure this out. When you give it any amount, like let's give it an amount of 10,000, it will convert that into an array of all of the powers of 2 that if you add all of these together, they will give you 10,000. And that's really useful for working with these mints because they all need you. If you want to get 10,000 sats from the mint, you've got to create outputs of 8192 plus 1024 plus 512. You got to create 5 outputs and have them fund each of them. So that's something you have to learn to do, and this function will help you do it. And then the last thing I wanted to show you is the references. So these are the nut specs right here. And if you go to the Cashu nut specs, they will outline, like in number 2, they outline what Keysets are and how to interact with Keysets. So basically showing you how to do this whole demo I did. So the nuts are really useful for continuing with the work we've done here and finishing your wallet. And then the blind sig JS library that I made You can use that. It not only has functions for creating and for validating uh, blind signatures, you can also create them with it. So you could actually create your own mint. You could code up your own JavaScript based mint using this library. So check that one out. And inside of it, if you go to its little repository, it shows you how to do all sorts of stuff with this library, including how to lock a token to a public key so that only the person with this public key can redeem it. And if anyone else tries to, they won't have the private key, so they can't redeem it. That's kind of cool. And then I also do multisig in here. With multisig, you can create a token and lock it to multiple public keys, like maybe 5, and say 3 out of 5 people need to co-sign in order to unlock this money. So there is multisig support in Cashu, and this is like, other than Fedimint, this is the only way that I know of to do multi-sig lightning payments. And it's kind of quasi multi-sig because it's actually just sitting on a mint somewhere. But you can use this library to figure that out. This is the BlindSig.js library, and everything's broken down for you in these little chunks. Like here's an example of a swap. Here's an example of locking something to a public key. This code right here. And so yeah, it's kind of all broken down for you and has some comments and stuff. So that's really useful. And then Gandalf rather, he created all this stuff with his Crypto.js library. I just made it compatible with the browser. So all kudos go to him, and you can read his documentation if you want more info on how his library works. And then there's the awesome Cashu library that tells you all about all the cool tools available. These are different Mint backends. If you want to use one of those, you can do that. Notice there's none in JavaScript yet. So we've got Python, Rust, another Rust one, and Golang. Somebody make a JavaScript one, yo. We got the libraries for it. We just need to make it. Then we got different wallets for doing stuff with Cashu, libraries. This is all awesome. If you love TypeScript, you're a jerk, but you can use that. Mine's not on there yet. Hey, Callie, what's up? I made an awesome thing. Give me some love, you know? So, yeah, this is all great. And that's it. That's the presentation. I hope you enjoyed it. Thank you all for coming to the Cashew Workshop. Woohoo! And I don't know how to stop the recording back there, but I'm going to go try.